welcome, John, to your Tiny Desk Convention live Q&A with moi. I'm super excited to have you here, and your arm that keeps, yeah, exactly. It's like in
Well,
frame.
I'm trying to get the good lighting. All right, there we go.
Yeah,
this
it's
is it. Nat's
lovely.
hard at work right now.
So it's really great to have you. I'm super excited. Every time we bring a Tiny Desk adventurer into the room, it's exciting because you all do such amazing stuff. And I think it's really great to be able to showcase to the world, like all the kind of the diversity of what marine conservation entails, what techniques, the diversity of techniques, the tools, the questions we ask. And I think, last Tiny Desk adventurer, actually, Matt Leslie worked, with cetaceans, whales and dolphins, but also worked with, fossil whales. So that was really interesting. And that was like a nice way that it's actually quite a nice segue from him to say, like, moving into what you do, which is fossil corals, which is exciting. But to kickstart, I'm going to ask you to do a very brief Coral 101, if you don't mind, just because, sometimes I think people aren't entirely sure what a coral is. And I think coming from you can tell them a little fun fact about coral.
Yeah. Fun fact, corals are animals, which blows some people's minds. Corals are definitely animals. So they are closely related, if you want to imagine, to sea anemones, kind of jellyfish. They're in the Cnidaria family. But essentially, if you think of a coral as my hand, right, everyone pictures like a branching. I should have brought a prop. I'm in my house, so I don't have any props. That's actually a coral colony. So a coral is an animal, and the animal is usually about the size of your pinky nail, or like half the size of your pinky nail. That's called a coral polyp. So if you can imagine like a sea anemone that's kind of upside down, that's what a coral actually looks like. And then a coral colony, which is kind of like that big bush that everybody pictures, is actually thousands and thousands of identical coral animals that are all jammed together, living together in one big apartment. And they're all genetically identical because of how corals reproduce. They can reproduce by called budding, so they bud part of themselves off and create identical sister cells. And I think what confuses people maybe the most about corals is that they have symbiotic algae that live inside them. Symbiodinium clade algae. But the big thing to know is they have all these little plants, algae, that live inside their skin, or their, well, not their skin, but that live inside them. And these algae are able to photosynthesize sunlight because they're plants. And the excess photosynthase, so the excess nutrients from that process, are given to the corals. So the coral get all these extra energy, and the corals give them a place to live and recycle nitrogen back to them. So when you think of a coral, think of a tiny animal that looks like a sea anemone. When you think of coral colonies, think of like the big bush. And when you think of a coral reef, that's because part so exciting and super cool is that they calcify and they produce this calcium carbonate skeleton. So when everybody thinks of corals, they think of this like hard rock, which as a geologist, I appreciate. But that is actually just the skeletal part. So the coral animal itself lives on a top layer of this carbonate. And as it grows, it secretes more carbonate, and kind of grows like a big skeleton. And if you get enough coral colonies together, they form a reef. If a reef grows long enough, that's how you get permanent geologic structures such as the Great Barrier Reef. So you kind of go from your pinky nail sized animal to something that's theoretically visible from space. So, that's what a coral is. But importantly, a coral is an animal. So take that away. That's the big one. That's the
I mean, take all of it away, right? Like I think people don't realize that. First of all, coral is an animal. Quite often people will just think it's a rock, right? Like that's problematic because then we don't treat it with the respect an animal deserves, right? Like people stand on them because they're just like, well, it's a rock. So we stand on rocks all the time, right?
Yeah, whatever.
Yeah, exactly. And then people don't realize that they have these symbiotic relationships. So symbiotic relationships are relationships where it's kind of positive both ways. So the algae that lives in the coral will photosynthesize. So, it'll use nutrients and sunlight and produce, various things. So oxygen is also a byproduct. And then anything that's produced extra will be used up by the coral. So the coral feeds part of its food comes from that, and part of its food comes from just being
Yeah.
just kind of filtering through the environment. So
Yeah, eating. Yeah,
yeah,
and that's what makes corals, we call these mixotrophs usually. So we have autotrophs, which are plants, they get their energy from sunlight. Heterotrophs are usually animals like us, we get our energy from food. The corals in this symbiosis are mixotrophs because they have the ability to get energy from these two areas, which is like, think of you having plants living in your skin and you're able to just get nutrients from the sunlight. I mean, that's what corals have achieved, which is why they're super cool, but also why they've been super successful in these tropical systems and why they're, all over that
yeah.
part of the world.
And I mean,
Yeah.
that would be really handy, especially sort of in the times of like lockdown and stuff, right? When you can't, curfew in Sri Lanka, we couldn't leave our houses to go to the shops. If you could produce your
Yeah.
own food, I mean, in your garden is one thing, but if you could produce it in your own skin, right? Like that kind of would have solved a lot of problems, I think, right?
I mean, like, I've been studying these animals for a long time, and it's still the most mind-blowing part. I'm like, can you imagine if I love to eat, and I'm always trying to gain weight for weightlifting, and, like, if I could just gain energy from the sun, dude, that'd be so dope.
So easy. Just FYI, there was a comment. My dad just said, "Hi, Big John, Ash."
Hey!
He's watching there in the other.
If he's
They're in the
watching,
living.
tell him I said hi. Yeah. Oh,
Yeah,
awesome. This is so good.
that's
I miss
cool.
your parents.
So, okay, so you go. Of course, everyone loves my parents. But we were going to, so I was going to say, so you have these, living animals and these structures that, like you say, it's the laying down of calcium carbonate that creates like what we see, this, and they get bigger. Some of them are gigantic.
Yeah.
But, they're not, like, they're really valuable for telling stories, right? And that's kind of what your thing is, like using coral to understand what's happening today based on what's happened in the past. Can you tell us a little bit about that? Like, I think it's so exciting.
Yeah, no, of course. I mean, so the way I like to think of corals as a study system is I look at corals not for what they are as animals, but what they tell us about the oceans. And that's exactly kind of what you're saying about telling stories. So corals are incredible animals, symbiosis on their own. They create these reefs. Reefs are permanent structures. Because of that reef, which is a habitat, they then form a coral reef ecosystem, which brings in biodiversity from everywhere else. So this allows small fish to live and lay their eggs and hide away from predators, which then bring the predators, and then it allows algae to grow, etc. That's why corals are the most biodiverse place in the oceans. Now, that's incredible, and it's, biodiversity for many reasons is important. And but what's interesting is if you look at corals in this way, then you start to understand that if there are coral reefs, it must mean that the ecosystem or the marine environment they're living in is healthy enough to support corals. Because although they have this incredible symbiosis, they're very susceptible to change. So they're kind of particular. So they're like your moody sibling, right? They only have a certain range of good mood. That's how corals work, which is why you kind of only find them around the equator, around the world, right? Don't want to get them late at night after they've been like not sleeping. So I have a lot of siblings. So because of that, right? I mean, basically, if corals are growing and they're doing okay, it must mean that the ecosystem is healthy. We can use that in the reverse, as if we start to see corals being sick or dying off, as we're seeing now around the world. That's telling us something more, not just about the corals, but about where they're living, right? I mean, it must mean that the home they're living in is no longer supporting them. And what I do is I look at this change and I look at this coral story, but through time, because corals create this calcium carbonate skeleton. Just think of it as a skeleton, like bones. They can persist in the sediments over geologic time, and then people like me can come dig them up, and we can start to see what corals used to be in this reef ecosystem, and how that may have stayed the same or changed through time, and what might have been causing those changes. And whether or not they're natural, right? Because, ecology and nature is variable. I mean, by definition, it's always changing. But are the changes that we're seeing in reef ecosystems, theoretically right now, because of humans or natural variation? And that's part of what I do. So, I mean, I love the simple term historical ecologist because it really is I mean, everybody knows history. Everybody learns it in school, right? I mean, we learn about human history, our country's history, etc. All I do is learn about our ecosystem's history, and that's the easiest way to think about it. So it's fun.
Yeah, that's really super cool. Okay, so just a small side note. I was
Yeah.
browsing your website and I noticed that you've got a paper accepted into Science Advances, which is
Yeah,
super cool. That's very
Thank
exciting.
you.
I was like, oh my goodness, how do I not know this? I'm like some kind of nosy auntie. I'm like, why has he not told me this important information? But anyway, now I know, so it's fine.
Now,
trust me to those
I
around.
did tell you,
Yeah.
but it's sort of public, but everyone can know, doesn't it?
It's on your website, John. To me, that's
I know.
fairly
I know.
FYI. But congratulations. So to anyone wondering like why it's so exciting, Science Advances is one of the like top scientific journals in the world. It's, you know, not easy to get a publication. So your research has to be really telling an incredible story that is very scientifically sound to be able to have it published there. So this is quite amazing. And also it's like, you know, John is in his PhD. Like normally people will publish in those really high level journals after years of experience of publishing and stuff like that. So to get a publication publication right now is really like something to celebrate. So just FYI, we did celebrate unknowingly by eating cake earlier on today. So I'm going to dedicate the cake that I've already eaten to you. Thank you for the cake.
I appreciate that. That's more than I've done.
Yeah, of course.
I just like breathe a sigh of relief.
But so you know, we're learning about these systems, right? You go out there, and so your Tiny Desk Adventures video was, I mean, I thought it was awesome because obviously people can see what you do. There you go, Sheena saying whoop 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 whoop. Well done.
I see that. It's sideways.
You're getting lots of whoops all the way from Seychelles. So there you go.
Thank you so much.
But you know, so so the first thing when my team watched that video, they were like, did he carry that pipe, right? How is this the pipe that you use to core these old fossil coral?
Yeah, so here's a funny story about this method. So the method is we basically take a big pipe, we bang it into the ground physically, and then pull it out, and then it's filled with sand, so then it's super heavy. When I first started doing this, my master's work was in Guam, and me and my supervisor at the time, Dr. Kehoe Kim, who's an awesome guy, is not as big a stature as I am. And we had to go out to a reef in the middle of Guam. It was called Shark's Hole. It's in the middle of nowhere. So like you park and then have to walk 2 kilometers through the reef to get there. So I have like all these empty barrels on my shoulder walking there. We cored and then we had to walk back. And when you put 2 to 3 meters of sediment in a core, it's like 40 kilos. So we're just like schlepping back all the way. Science, right? Yeah. Woo.
Yeah, that's crazy. And so, but how heavy is the pipe without the sand to start off with? Because I felt like it's pretty heavy.
No, it's not. I don't want to be here like, oh, so strong. No, they're made of aluminum. Well, yeah, but that's neither here nor there. They're usually made of aluminum, so they can be quite light. And they'll range between 2 to 5 meters. The bigger problem isn't necessarily how much they weigh, but like walking around with 5 meters and knocking people in the head, and you know that's not ideal. Well, when I was coring in Panama, we had 6-meter cores. So they would be strapped to the side of the boat, and then we'd have to, like, as a team, stand them up and everything.
That's crazy. So you take these cores and you go to places, obviously, that you don't do this on the live coral. You're doing it in areas where there's, there's fossil coral or dead coral, right?
No, both, but also on live reefs. And that's what's great about this method is it was created, or the whole purpose that it came about was, one, it can go anywhere. It means you don't need much. You need a pipe, a hammer, and somebody like me, and then you can kind of go to all these. And when you're there, you're not damaging the surrounding animals, right? Because we're just like you think of a straw, and you're sticking a straw in the piece of sand, right? So we're just sticking a little straw in there. We're not bringing in a generator or a big core, or taking a backhoe out, or I think of excavating fossils on land. So it's actually real for that reason. It's simple, so you got to give one or the other.
Yeah, that's crazy. So yeah, so you go into places where there are live reefs, but you don't use the technique on a live coral. You use it on the places where the live coral isn't. Is that right or no? Am I wrong again?
Yeah. So usually, so when we say a reef, that means typically you pick places to core where you know there are live corals living on top of a history of dead. Coral dies, it just falls over, another coral grows on top, it grows, and it builds up like this. What we're the reef. So we want to, I mean, I have cored places where live corals no longer exist to see why that might have occurred. But usually you core places where corals are still alive, you go through that reef structure, everything below it was coming from that same reef just back in time.
Okay.
But yeah, we're trying not to take live corals out. I mean, this pipe can kind of maneuver its way right in there. Right there.
Yeah. Yeah. But I mean, it is intensive,
Makes
right?
sense?
It's not, yeah, absolutely. So you take it and you
Okay.
basically underwater. I mean, you're doing this on like just snorkel gear. So you're not scuba diving. You have to kind of free dive, get down there, hammer. Ooh, I think you're back. Okay. Just don't move so much. I know. Joking.
I'll just stay here.
Yeah, right. There might be a little bit of a delay. So, guys, if there's any problem with the sound and stuff, just put a comment in so we know, if you've missed anything or if nobody can hear us. So please feel free. But, okay, so you go down there, you're free diving, you take this long pole, you have to go use a hammer, bang it in the ground, and you have to take it in turns with someone because obviously, like, you can't do it on one breath, right? Like, so you're both taking turns, or can you do it? Please don't tell me you can do it in one breath because I'll cry.
No. Okay, so so the video in the video that I made showed doing it with snorkel. So in really shallow reefs, we try to snorkel. Most of the time, I actually like to do it with scuba gear, under scuba, just because you have the freedom to be under there longer. I definitely cannot do it in one breath. And funny enough, although I may be a great hammer, like my nickname's the Hammer, I suck a lot of air. And I don't know if you guys are scuba divers, if anyone on here does scuba, but when I'm working, I'm like cooking through tanks of air to bang. Because, yeah, I mean, quite literally, I just have a big hammer and I'm pounding it down into the ground, but it just happens to be underwater. So I prefer to use scuba, and it makes things a lot easier because then you can bang it in, cap it, come back up, change your tank, go back down, etc. So it all depends on how deep the reef is.
Yeah, and it makes sense. I mean, you are like about twice my height. Small exaggeration, but you're
probably like twice the size. Yeah.
Yeah, exactly. And you're like, exerting underwater. So you will suck up more air, which is kind of natural. So then you have to bring this. I mean, the thing is, you have to think about so many things. I don't know how many of you out here are scuba divers, but you have to constantly look at your air. You have to make sure, you're not like, you have to keep track of so much. And then on top of that, you have to make sure you have enough air so that you can actually cap it and also bring it up and take a safety stop probably and then come up to the surface, right? So there's a lot of it takes a lot of focus and concentration and just being a lot of self-awareness to do the kind of work that you do, right?
Yeah, it's definitely what's called tech diving. I mean, it's pretty technical. And I mean, you have the buddies, and usually I would say we usually core with a team of 4 people because when you first start the core, it's good to have people holding it, and then it's just good to rotate and have support. But no, you're right. I mean, I take scuba diving very seriously. I know some people are pretty, Wild West about it, but I take it very serious, but it's because there's a lot of moving parts. But usually, you're okay. And thankfully, corals tend to exist in shallower water. So most of the dives and most of the coring dives I take are shallow enough where I'm not really scared of depth of an issue. But I have done a couple of like deep cores, and it's yeah. And then you go through air faster. So yeah, I mean, it's all part of the job. I don't know.
Yeah. Okay. And so,
But you
okay,
got to
by
be
using,
smart.
sorry, what's up?
I just said you have to be smart
Yeah, you
about
have to
it.
be pretty smart about it. Okay, so so you've done, you use this technique, and you do a lot of things. What kind of things have you found using,
Yeah.
your brute force and your pipe and hammer?
Yeah. No, good question. So what's the coolest thing that you find when you look at a core, right? So you take the core, it's like, woo, you get this whole straw. I always tell people, I think of it as like, if you guys drink bubble tea, it's like you fill the straw up with little bubble tea bubbles and then you dissect it. And you open it up, you separate it into little like jars of sediment, and then you dry it, and you're like, man, this just looks like dirt, which it is. Well, sediment. But then you dry it, and I put it through a big sifter, and you sift it, and the second it goes through the sifter, all the different cool taxa start to come out. And at the top, it's like big pieces of coral or big shells, rocks. I like rocks. And then as you start to go down, you'll start to see big sea urchin spines. You'll see smaller micro gastropods, so smaller gastropods. And then when you get in a microscope, which is super sweet, in a dissecting scope, you're going to start to see really tiny sponge spicules. You'll start to see sea urchin spines, fish teeth if you're looking for it. One of my closest friends and colleagues, Erin Dillon, she looks at shark dermal denticles. So sharks have, like, if you think of it as shark scales that are they're microscopic, but they shed on the ground. And in the sand, she can collect and look at shark denticles and ID sharks of the past too. So, I mean, I've called it a time capsule before, which I don't think is an exaggeration, because you just have this incredible mini, snapshot of an ecosystem. And for me, that's the coolest thing. And then what you do with that data is, the stories you can tell. And unfortunately, the ones that, I have been looking at and telling, and I'm sure most marine people around the world are telling the similar stories, just looking at human impacts and how those have changed or shifted ecosystems. And in Hong Kong, as I said in the video, it's similar to many other places in the world where we're losing these branching corals, which tend to be fast-growing, high carbonate producers, really complex, so they create habitat, but they're very susceptible to changes. So in my cores, I see a lot of those in the past, and then now, if you were diving in Hong Kong, you would see very, very few. So it's these compositional shifts that you start looking for. There's many other things you can do, but I
Interesting.
guess yeah.
Yeah. So can you so you've found some changes in Hong Kong, and can you talk a little bit about how your work, tells the story of what went on in Hong Kong in terms of all the anthropogenic impacts and stuff like that?
Yeah, it's cool. So I'm excited. So for that paper that will come out, and maybe we can link back up afterwards when it's a fish. I really like it because one good thing about Science Advances, or among others, is they don't have a small word limit. So I dumped a lot of historical research into there, which I really like because it almost reads as like a monograph of historic impacts in Hong Kong. And this work that's being published really tells the story of like the corals and the biodiversity losses and the compositional shift. And then if you paired with other work out of my lab, and then I was a co-author on another paper by Nico Dupre last year. He's looking at isotopes in the coral skeletons, which I also do. And you put those together, and what we've shown is that really the biggest impact. One sec. The biggest impact. Yep, isotopes.
Yes.
Yeah, yeah. I was
Break
gonna
it
do
down.
that in one sec. I'll say what
Okay. Go.
isotopes.
Go. Go.
Basically,
Yeah.
we've used these methods to show that the biggest impact in Hong Kong has been water quality and water pollution and too many nutrients getting to the ecosystem, which is throwing off that clean water balance that corals need. So yeah, So when you ask me the question of the cool stuff you can do in cores, there's like the fossil stuff, and then I'm also a biogeochemist, so I work a lot with stable isotopes. So isotopes, for anyone, if anyone is not chemistry savvy, are elements. So if you take, for example, oxygen, everyone, we know what oxygen is as an element, but oxygen has different isotopes, meaning they have different amount of neutrons in the nucleus of that oxygen molecule. And a neutron has no charge, it just weighs more. So protons are positive and neutrons there. In the nucleus, you have electrons that move around. So isotopes are different species, if you want to think of it, of an element with different neutrons, meaning they have different weights. And that's all cool. Everyone's like, that's sweet, John, I don't really care. What that does, though, is that makes different amounts of these elements in the world. So oxygen 16 versus oxygen 18, that's how much it weighs. And then you can use these isotopes to say different things because they behave slightly different biomechanically. And the easiest way to think about it, and I'll keep it at this, and then we can move on, is if you have two elements and you're a system of energy and you want to do something, it's easier to work usually with an element with less neutrons because it's lighter. If you just think of pushing a rock up a hill, it's easier to push a smaller rock than it is to push a bigger rock. So because of these biases towards different different isotopes, we can then use their ratios and look at them and be like, oh, the ratio is higher or lower here. That must mean something different or whatever.
Okay.
And yeah.
No, keep going.
Oh, I was just going to say, the one that I think people can most comprehend and probably are most familiar with is how we know about paleo temperatures, right? So I'm sure like most people listening or in the world have seen that graph where it's like, oh, temperatures, then they skyrocket, right? And then if you look in temperatures for the last million years, people are like, oh, we got those from ice cores. And everyone's like, cool, it must have like licked the ice core. And it was like, that's how cold it was when this was formed. What they actually did was they took the gas trapped in the ice and they measured the oxygen isotopes because the ratio of 16 to 18 corresponds very closely with Earth temperatures. So as we look at the changes in isotope ratios, that actually tells us the changes of temperatures through time. And that's one way it can be used.
Cool. And so we use also carbon isotopes to date things all the time, right? Like trees and stuff like that. You can get so much information based on what was present in the past versus what's present in the present.
Yeah.
Present, is that right?
Present.
Present. So I got a question from Penny, and she says she would love to know what's the furthest date back in time you've seen your cores, which I think is a great question, actually. And how far can you go back with your cores, but how far back have they gone with these cores anywhere in the world?
Yeah, no, that's a great question. Hi, Penny. Great question. So it's all dependent on a fancy term called accretion rates. And all that means is how fast and thick does a reef grow, right? So if you imagine a reef that grows really, really fast and productively, just like a human that's really, really, really tall, if it grows faster, it's going to accumulate carbonate faster. So when you core it, it's not going to be as old as it. But if a reef grows really, really, really slowly, and it's like 1,000 years, 2,000 years, 3,000 years, when you take that same length of a core, because the core length usually doesn't change, you're going to get a lot more. You're going to go back a lot farther in time, but you're going to get less resolution because the dates are going to be very close together. So in Hong Kong, I've taken up to about 3.5 meter cores. And some of the dates I have go back 7,000 years before present, so before today. So that's 5,000 BC, which is really cool. Which is sweet because that's in this part of the world. We're talking that's right before major rice cultivation and agriculture really moved into where Hong Kong is. So it's interesting. It's a long time ago. In cores in Panama, because reefs accrete a little bit faster, we have to take bigger cores, longer cores, excuse me. So in a 6 meter core, we went back anywhere from 4,000 to 6,000 years in the past. But it's very variable. Usually you have an idea before you're coring, but you really don't. We say this a lot, but it's like you don't know until you stick a pipe in the ground. Like who knew 10 years ago, or well, no, maybe 100 years ago there were no coral there, and you core and then you get nothing. So
Right.
it really depends. But this method, and now that we're going to talk in the paleo, the deep time range, I guess this method is to look at Holocene changes. So the Holocene is since the last glacial maximum. That's like 12,500 years ago. So to my knowledge, no one has gotten breaking up.
Yep, you're breaking up.
To my knowledge, no one has taken this method, sediment push cores, and gone back anywhere like farther than the Holocene. So we're talking the last 10,000 years. Most reports I've seen are in the range I'm talking about 1 to 6,000 years in the past. So
Okay.
that is the range.
Okay, so just I want to touch on what you said, right? Like, so when you do the coring in Hong Kong, okay, so you can go back 7,000 years before the major sort of rice agricultural, rice agricultural scene happened. So
Yeah.
what is the difference, before rice agriculture came in and then post? Can you see a distinct difference? Is it like a change in water quality? Is it change? Do you see those changes in the data?
Yeah, so there's two big changes I would say that it's a royal we have seen. Personally, you'll see there's a pretty distinct change in sediment. So sediment, the dirt that it's growing in grain size. So that's how big or small each piece of sediment is, how big the sand is. And because Hong Kong is right next to the Pearl River, which is it's like top 20 biggest rivers in the world. I can't remember. Which is why a lot of people settled on it in China. As agriculture is happening upriver, you have to clear land, you have to plant plants, and by doing that, you're eliminating vegetation, and that's bringing sediment into the river system, which is then dumping out over Hong Kong. And terrigenous, so land-based sediment tends to be finer grain than marine, so we can actually see that, and we can see this added terrestrial sediment in the ocean system. People at university, not myself in the earth science department, look at pollen, and I can never say this word. They're pollen. I don't know what it is. I think I just froze. People who study pollen, I can never remember the word. Whatever, it doesn't matter. Have looked at the change in pollen in the sediment, because pollen coming from trees is different than pollen coming from rice plants. And they can actually see traced in the sediment this change, which is how we know. I mean, it's not based on coral data. It's based on this awesome work where people are looking at microscopic pollen. And that's another clear indication that we can see this change to an agricultural system. So, it is incredible, the signatures that you can see in cores like this. So it's pretty cool.
It just.
But,
Sorry.
Oh yeah, no, go.
I was just gonna say,
like,
it just goes to show that, and I would let you continue. Sorry, but to show that, we're walking around on history, right? Like, that's the one thing we have to remember. So there's clues to our past everywhere, and it's just knowing how to look for it, and of course knowing the techniques and technology and stuff like that makes a difference. But it is something that we have to remember, that what's under our feet is not just something that just appeared today. It tells a story, right?
Yeah, no,
and
of course.
That's what your teams out there do a lot of. Keep going.
Yeah, exactly. That's what do you want? What do you want?
Trust me, people never stop wanting stuff. So I wanted to say, we had a question, and guys, you know what? Like, it's been 40 minutes, and I would love to give you all the opportunity to ask questions. So if you do have questions for Jon, just type them out, and I'll ask him in between his frozen wheel of death face. But if you stop moving so much, I don't know if that doesn't do anything.
I
But
don't know if that's doing anything.
Sheena wanted to ask if it's possible for you to summarize just what you found in the paper that's just about to be published.
Yeah,
Or is
no,
it
yeah. Yeah, I can I mean, I've given this talk at conferences, so that's fine. I mean, I actually tried to summarize it briefly in the video, but essentially the coral environment in Hong Kong today is much different than it was in the past. And we think it's much different than it was in the very near past. So within the last 100 years, we think there's been a complete shift in the ecosystem. And if you think of Hong Kong, you don't need to know the geography of Hong Kong. All you need to know is there's an eastern region and a southern region in the marine world. And right now, all the corals basically exist in the eastern region because that's where we have ocean water that flushes in and out, which essentially cleans it. On the southern region, we have the Pearl River that dumps out directly into that area. So not a lot of coral and anything else. Think of coral as a proxy for biodiversity. So we have less biodiversity as we move closer to the river. We see that now. One of my main questions when I got to Hong Kong was, has this always been the case? And it's possible to think that it wasn't humans because a river is a big system that could be controlling the environment just because of fresh water and natural inputs. So took corals all over Hong Kong, and what we found is recently, not only did the biodiversity that exists in the east used to be a bit higher, it used to extend all the way down into the south, much closer to the river. So essentially, the habitable space, so the habitat where corals can grow, has shrunk by almost 50%, we think, in Hong Kong. And the biggest change we've seen, so there's a decrease in size where corals can grow, which, if you think of it, means a decrease in area where this high biodiversity can exist. And then also, the corals we've lost the most of is what I was talking about before. So it's these branching corals, which are I can't emphasize enough. I mean, there's a great paper out by Renema in 2008, also in Science Advances. Essentially, for the past 2 million years, these branching acropora corals have been the corals in most reefs around the world. And that's because they grow fast, they do really well in high light environments, and they grow really fast, sorry. And that creates habitat, that creates biodiversity. So by losing that, we then lose this entire reef system, and we're left with what's called massive corals. So these are corals that kind of look like rocks, and they don't freeze. Okay, good. And they just create less space, less surface area. So we've shrunken where corals can grow. We've also, and the final piece of the story in the paper is we've linked it pretty strongly to water quality. And that's important because when you think of conservation and you think of how we help these different areas, you want to be able to do something. And global climate change is a massive impact all around the world. And although people pretend to debate it, all scientists agree on it, and we know what has to be done. We need to decrease carbon emissions. We need to lower the global temperature. But there are these things that can be done locally or regionally that can relieve stress from marine environments while that's happening. And what we've shown is in Hong Kong, the number one thing we have to clean up the water quality. Because of the raw pollution and the pollution that's being dumped in there, it's worse than climate change. We actually haven't seen any documented climate, so heat impacts in Hong Kong yet, because we're globally pretty far north. It's all local stress. So if we can relieve that and give these animals a chance, they're going to fare much better in the future, while the Earth inevitably changes due to climate change. And so that's kind of the three parts of the story in summary.
That's incredible. That's awesome. And it's and that's what I want people to appreciate. Everyone out there, I want you to appreciate how much we can tell from what's around us, right? Like sometimes we kind of look beyond our local spaces or beyond these spaces to find answers, but it might just be under your feet. It might be something that's just around you. And I think thinking about it like that, there are so many stories to tell, and interesting stories. And you sometimes don't even think about, like, John's going underwater and like smashing a pipe into the, the kind of old coral and he can build these stories, but also there's this element of collaboration, right? So like John said,
Yeah.
like earlier, understanding when the rice agriculture started is not what he can find out, but it's what his colleagues can find out. People who are polynographers. I don't know. That's what we're going to call them. Okay.
I want to like Google search it.
I think you may have. Don't do anything on the internet right now because we're going to lose.
I'm not. Yeah.
But just so you know, that element of collaboration is what allows these stories to become more complete, and that's what gets published in these bigger papers, is that they want complete stories. They don't want a piece of a story. They want to know, tell us the entire story. So if you're a student out there, this is something to think about. But in general, with anything we do, like, there's never a complete story if we're leaving people out of the conversation. And that's obviously something I can go down a path forever, but just really like being aware of that. I'm going to just, I had a question from your map loving beard twin, my father, and he wanted to double check, what is it that you're using for dating your coral? What's the isotope?
Oh, yeah. See, your dad, the man. So there are two ways we can date. We can carbon-14. Okay. So before I talked to you guys about stable isotopes. These are isotopes that aren't bad for you. They're stable as in they don't degrade. Then there are unstable isotopes, and think of atom bombs, right? That's what makes those. So one of those is carbon-14, which radioactively decays, and that's typically how people date carbon-based entities. Archaeologists, trees, bones, most things people do. A lot of it is. There's a newer technique called uranium thorium dating, or uranium series dating, where there's trace amounts of uranium, things like coral skeletons, and as that breaks down, you can use that. And what's interesting and what's nice about this is, one, the precision tends to be much higher. So 14 dating, you can usually get a date plus or minus 50 years, or 30, which if you're looking 7,000 years in the past, it's like, okay, cool. If you're trying to figure out something 200 years ago, it's a bigger deal. Uranium thorium dating can get down to 1 year. It can identify the year it happened. So it's a little bit, and it's much more precise. So we've used both to date my course.
Cool. Okay, cool. Oh, very cool. I'm sure my dad will be really pleased. Good question, beard buddy, and map loving buddy.
No. I think it's as important to be collaborative as it is to be interdisciplinary. And what I was saying is, as a historical ecologist, I'm not just an ecologist. I'm a geologist, anthropologist, archaeologist. Not to take anything away from people who do that full time, but dipping your fingers in these other disciplines has really enhanced my science in every way, because then it allows you to think in different ways. And that's how I was able to piece this incredible story about Hong Kong together, is from thinking of those different angles. And I only bring it up because when I don't know, Asha, I don't know if this is the same for you, like when you were going through Oxford or whatever, but when I first started as a geologist, there was still this idea that like interdisciplinary science was kind of like frowned upon. All the old scientists were like, no, you have to specialize. Like if you're a chemist, or you're a physicist. There's no, like, we don't talk to anyone else, which is crazy. That was only, when I first started uni. And now everybody's like, interdisciplinaries, what's up? And it's the new thing. And I just like to encourage it because it's the only reason I've been successful. I'm not like a great geologist. I'm not a great biologist, but I've been pretty good at bringing a bunch of those disciplines together. And I think it's really important.
I fully agree with you, because I think, my time was a little bit before your time. So definitely it was even more archaic at that point. But certainly I think, even the strength of kind of things that I do is that, I'm a marine biologist, with a strong biological background where I understand biology. I understand how animals behave and, things like that. But I chose to do my PhD in an oceanographical lab, and it was, physical oceanography, which is the circulations, currents, really foreign stuff to what I was doing. But I realized that if I didn't cross that boundary, if I didn't work with, you know, the people who understood that stuff and kind of brought it together, I would have no story, because I wouldn't be able to understand. Looking at why the blue whales were staying in Sri Lanka throughout the year is impossible if I wasn't looking at how the environment was shaping that and why it was driving that, right? So for me, it was absolutely necessary to take that step outside and like have a look at that. And, you know, we are always trying to build pictures of the past. Like, you know, how long have the whales been here? Like, because people will ask me, did they just arrive in 2007 when the whale watching started? No, actually, the first map of the world by Ptolemy, you know, the most significant part of his map was like Sri Lanka, which is a weird shape, but there are these coordinates that are actually accurate. And, you know, the Sectum Promontorium is basically off the southeast coast, where I actually saw my first whales. And Sectum Promontorium means cetacean promontory. Cetacean is a collective term for whales and dolphins. So the point being that I think it's about being curious as well, right? Like, because if you're curious about all elements of it, then you start to build these incredible stories that are way more powerful. So I'm totally with you about encouraging collaboration, but collaborating. And, you know, people said to me, they're like, why didn't you go into a marine mammal lab? Because you're studying marine mammals. And I was like, why would I go into a marine mammal lab? Like, that's the one discipline that I'm comfortable with and familiar with. Whereas I don't know anything about oceanography. So I'm going to challenge myself at this stage to learn new stuff. You're frozen, but you're back. But yeah, so I think I totally agree with you. I want to just touch on one quick thing. And I know, you know, it's like been an hour and I don't want to keep people waiting, but I do think while you're recovering from your pause, I have a question just really quickly about like, what is, you know, can you tell us briefly like what your route was? Like, you know, your background is not in marine sciences per se. You're a geologist, right? Like, that's how you began. And I think that alone tells us a little bit about your interdisciplinarity. And I think like, I think it would be really interesting for people to know that you didn't have this straight path, but you just sort of went, and you've kind of brought all your loves together. So can you tell us a little bit?
Sure. How far back you want to go? I mean, I was born in no, just kidding.
Whenever you had a beard, start from the time when you had a beard, maybe.
Well, I was born and I had a beard. No, just kidding. No. One thing I do love to bring up is, you know, I never thought I was going to be a coral reef biologist. I mean, and I work with a lot of people who love coral reefs. They've been studying them their lives. They used to go scuba diving as a kid. And I think that's not been my path at all. So I went into university as a psychology major, which is very different. I thought I wanted to help people. Turns out I wanted to help nature. Eventually, throughout my 4 years there, I ended up getting a degree, and that was mostly, I'll be completely honest, that was because I went through 2 years of hard science for my psych and then my bio-psych degree. At the end of those 2 years, I was like, well, this isn't what I want to do. I don't want to go to med school. And I worked at the dean's office of our university. I was like, so what can I do? And they were like, well, have you thought about earth science? And I was like, I'm from a very small town. Like, earth science and geology wasn't really a thing. You had like a certain thing you could choose. And I was like, what is this? And they were like, well, you study outside. And I'm like, I can be outside and study rocks, and that's a degree. And they were like, yeah, totally. Loved it. It was stuff I loved and did anyway. I already had the background in chemistry and biology at that point, and I lateraled in. So that was how my degree in geology and environmental science came about. Afterwards, I worked for the federal government for 5 years, and I just worked hard and said yes to any project I could because I just wanted to gain experience. And I did everything from engineering to remediation to environmental science to geology. The wrong term, but what I really found most fulfilling was the areas where humans and the environment mixed and where humans had a detrimental impact on the environment. And I was interested in those systems. And by far, the work that I did, the biggest system was always the marine habitat or the ocean that we saw the greatest impacts. So when I decided I wanted to go back for a research degree, I wanted to get a master's to get more research experience. I essentially cast a wide net and started emailing people. And there was a guy, Kehoe, who was looking for somebody with a more geologic historical ground to test out this kind of historical ecology idea. And he was a coral biologist. I obviously knew a lot about coral because they're important animals and how they're indicators of ocean health. And I was like, yeah, like, here's what I'm good at. Here's what I'm interested in. He's like, cool. I don't know anything about biologists. Got into it with my master's, hit the ground running. And so my master's, and then I really, when I came for my PhD, I wanted to go to a place that gave me three things, like support academically, and I have an incredible lab, an incredible supervisor, opportunities to diversify my research, well, both humans and research, actually. China's a great place, and isotope skills, all of which I've done. So I came in calling myself a historical ecologist because that's really where I've been able to pull in all this info. And that's how I got here. And then from here, it's just been collaborating with local archaeologists and talking to anthropologists, and then talking to people who really know, who really know ocean chemistry, and biologists who know the molecular backbone of corals. And I just kind of use that diverse background I've definitely accidentally stumbled upon, and thankfully the science gods were nice enough to name something historical ecology so that I had a degree at the end of it all. They were like, well, let's throw this kid a bone. We'll just call him a historical ecologist. It's like everything. So it's been really great.
That's really cool. And I love it. I mean, I think this is a great point to wrap up. But what I want to I always try to draw parallels between my path and my tiny disc adventurous path, because I think that makes people realize that actually our paths are all there are elements of our path that are similar, right? I had a sense that I wanted to go into the marine field. My undergrad was in marine biology, but I didn't necessarily know what I was going to do. And then I stumbled upon these whales, and then it became these whales. But I cast a very wide net as well, because marine biology, as much as people think, a lot of people think, oh, it's whales or it's corals. It's so many things. We do a lot of work with fishermen, for example. We look at the social side of things, and we do, so there's a range of things. And also actually, one of John's, a part of his project, we sort of supported him locally, because he's looking at some comparative work with Hong Kong and Sri Lanka. So, it's of interest to us to support and be in a part of these projects that can tell us more about our environment as well, and also help to give opportunities to other students locally to learn more things also about our oceans and stuff. But I think, one thing we have in common is that I also didn't go straight from undergrad to master's to PhD. I also took time out. I worked in between. And I think that's kind of a key thing that you also did, which is exploring what it is you want, so that by the time you get to your PhD, you know what your 3 wants are, right? You're not. And so I think I want to wrap up with a piece of advice to anyone who's watching, who's considering this career path and where to go. Don't rush life. I always say life is short but long, right? So, you don't have to start a PhD by 25 to be considered useful to the world. You have to start a PhD at the point in time when you can be useful to the world, when you can make a difference. And that can come at any time. I started my PhD at 30, so I was pretty late to the game, but it didn't hinder my progress, and it hasn't made me a lesser scientist as far as I can tell. So, so I want to just say that, it's been fantastic. I mean, I could talk to John forever. This is kind of my Achilles. I bring in these tiny adventurers who I absolutely love what they do. I think they're so impactful in the world. They're so important to the world, doing amazing things, and just showing us that, one thing is, the world is an incredible place, and we underestimate how amazing it is often. But if we dig deep and we start looking around and we really open our eyes to what's going on, there's just so much fascinating, fantastic, magical stuff. And I think, we learn so much from all these people. You're getting a lot of thanks from, we have Navika, who's our really our huge ardent supporter, 8-year-old Navika, sharing career stories. Thank you very much. Penny says thank you for a super interesting adventure into historical ecology. Sheena, thank you, lovelies. This was fabulous. Thank you, all of you, for coming. This for me is magical. It's a great opportunity for me to sit with friends and people I really respect, and have these conversations and have you guys sort of like jumping in. But you know, I think I could keep talking to these people forever, and I'm sure I hope you all learn something and gain something, if nothing else, just the self-belief that, you know, we all have our individual stories, but we all can get there, and we just have to work. So with that, as I wait for Jon to recover from his slight pause in his, yes, again, I want to say thank you so much, Jon, for joining us. My enthusiasm, excitement keeps getting buffered by his slow internet. Jonathan? Hello. But yes, thank you very much. Thank you to all of you. Oh, you can hear me. Okay. Thank you to everyone who's joined, and thank you for coming back when we got cut out, and thank you for, you know, bearing with us. But also thank you so much to Jon and for doing what he does and telling us the stories of, you know, the deep, using a hammer, a pipe, and some coral. Thanks, Jon. You're still paused, but I think we're going to get there. Okay. Thank you.
I heard all that.
Bye-bye. Speak to you soon. Okay. Perfect. You want to say bye to everyone, and then we can bye.
I just want to say bye. Asha said it all. Just remember, you all bring something to the table, and you don't know what it is yet, but just my advice, as always, is work hard and be nice, and you guys will figure something out.
That's right. Work hard, be nice. If you have a beard, flaunt it.
Keep growing. Right. If you go to the gym, that's cool too. Yeah, but you do you. You do you.
Exactly. All right. Thanks so much, Jon. I'll see you soon.
Thank you, guys. Thank you so much.
Bye.
Bye.